Okay, so we've got a couple more examples to consider. In this one of the things you'll notice that sets it apart from the previous two examples is that there's actually two occurrences of x. X appears on the left-hand side, but it also appears on the right-hand side. But don't worry, that's still no problem. We have a method for handling that. All we need to do is subtract from both sides. Now we could subtract 3x from both sides, or we could subtract 2x from both sides. Either one is going to work. I'm going to just choose to subtract 2x from both sides. Okay, so what will happen if I subtract 2x from the right-hand side? Let's start with that one because it's more straightforward. If you have 2x and you subtract 2x, anything minus itself is just going to give you 0, right? But on the left-hand side now, what we really have is 3x minus 3. So if we have 3x and we subtract 2x, we're just going to have 1x left, right? If you have 3 pencils and you take away 2 of them, you just have 1 pencil left. That's what I always think about. So that's how we can start this. So 3x minus 3 minus 2x, that's going to give us just 1x, but of course we still have that minus 3 there. Okay, so that brings us to this step. So now this is good because now the x only appears on the left-hand side of the inequality, and we just need to get that 3 over to the other side. So we'll do that by adding 3 to both sides. So we'll have x is greater than 3, because if you add 0 plus 3 is 3, right? Okay, so there you go. Now we're ready to sketch the solution set. So if it's just x is greater than 3, well then you can just say, okay, here's 3, and we want an open dot because we're not including 3, and then we want to shade all the numbers to the right. So that's the picture of our solution set. And in interval notation, we can say this is 3 to infinity. Okay, so that wasn't too bad. So yeah, if you have a term on both sides of the inequality that has an x, you have two x terms, one on either side of the inequality, just subtract one of them from the other, right? We could have subtracted 3x from both sides. And then what you'd end up having is you'd end up having a negative x on the right-hand side. So, and you could still handle that as well. It would just be an extra step. So that works as well. Just if you have a term on both sides of the inequality that has an x component, then just subtract one of the two from both sides of the inequality, and that's how you can handle it. Okay, the last example here, this one's different as well, because it's not just one inequality anymore, it's actually two inequalities, but they're just written simultaneously. So what you have here is you have 1 minus x is sandwiched between the 0 and the 3. So actually, no problem. We can handle this in the same way. We just have to understand that we're working with two inequalities. We've got 0 is less than 1 minus x, and we've got 1 minus x is less than or equal to 3. And just understand that we're working with two inequalities at once, and anytime we do something to one side of either inequality, we have to do it to both sides of either inequality. So in other words, just think of it this way. Here's a simpler way to think about it. You have three sides in a sense, right? You've got a left side, a middle side, and a right side. Whatever you do to any of those sides, you have to do to all three. It's as simple as that. Okay, so how about we start by, well, what's our goal? Still the same, right? We want to get that x by itself. So right now it's 1 minus x. So let's get rid of the 1 first. We'll subtract 1 from all three sides. So we'll have negative 1, negative x, and 2, right? That's what I get if I subtract 1 from all three expressions. So now I don't have the x by itself just yet. I still have that negative sign to deal with. So we need to get rid of that negative sign, and we'll deal with it in the same way that we dealt with the negative sign in this case. What did we do? We multiply both sides by negative 1. So in this case, we're going to multiply all three expressions by negative 1. So if I multiply negative 1 by negative 1, I get positive 1. If I multiply negative x by negative 1, I get just x without the negative sign. I don't want to say positive x because x might actually be negative. We don't know. X itself could be negative, but the most important thing is that that negative sign is removed. Okay, so we multiply negative x by negative 1, we just get x. And if we multiply 3 by negative 1, we're going to get negative 3. And you see that I've left the signs blank. I haven't drawn the inequality signs yet because remember, if we multiply by negative, which we just did, we have to flip the inequality sign in both cases. right? So we're going to have to flip both of those inequality signs. So this one was a greater than or was a less than or equal to sign. So now it's going to change to a greater than or equal to sign. And same with this one. It's going to be changed to a greater than or equal to sign as well. And that's as good as you can do because you've got the x by itself. But you may want to rewrite this so that the smaller quantity is on the left. So it looks more like an inequality that defines an interval, right? So I've just rewritten everything so that the smaller ones start on the left. So it's the same inequality, just expressed differently. So we still have x sandwiched between -3 and +1, but now it's clear that that's the left endpoint and that's the right endpoint of our interval. So when we go to sketch the solution, we'll have -3 over here, +1 over here. We want a solid dot for both since they both have non-strict inequality signs. And then we're going to shade the points in the middle. And that's our interval. And if we write it in an interval notation, we can say -3 to +1, and we want square brackets on both, of course, since we're including both endpoints. Okay, so by the way, one last thing before we move on, or to complete this section rather. Why are they called linear inequalities? Okay, it's simple. Because there's no complicated operations like squareds, there's no cubes, there's no square roots. Look at all these inequalities. All they have is just constants, or they have a variable that's multiplied by a constant. There's no, and in fact, in all of these cases, the variable is x, but there's no reason that it has to be. It could have just as easily used the variable y or z or anything else, right? But the point here is that all you have is variables that are multiplied by constants, and then you have constants added or subtracted as well. And this is multiplied by a constant as well. That's x multiplied by -1/2, and so on. So that's why they're called linear inequalities. You can certainly solve nonlinear inequalities as well, but it's harder.